Good afternoon, everyone. My name is Karen Yang from National Tsinghua University in Hsinchu, and thanks all for being here till the end of the session. And I believe everyone is pretty tired and hungry now, but please bear with me for the next 15 minutes. So today I would like to share with you about our recent simulation study of understanding the core-core, non-core-core dichotomy, especially looking into the interplay among mergers, cooling, and AGM feedback. And so the system we're interested in this in the background image here. This is a beautiful image of the Perseus cluster, and this is constructed using the edge detection technique to highlight the features. So the Perseus cluster is a very famous core-core clusters where we can see clear interaction between the gas and also the injection from the central AGM. And in the Perseus cluster, there's also this beautiful spiral structure. We think that is due to the sloshing motions of previous cluster merging activity. So this is kind of the system where we can really understand the interplay among the different physical mechanisms. And in this talk, I will be mainly focusing on our understanding of the core-core and non-core-core dichotomy. So first of all, let me just give a background introduction. So we know that in the universe, the clusters are basically divided into core-core and non-core-core clusters. The core-core clusters are typically having very short central radiative cooling times, and because of radiative cooling, so they usually present very low central entropy if we look at the entropy profiles within all clusters. And so if we compile a sample of clusters and plot the distribution of the central entropy, then we find that the distribution is typically bimodal. So therefore, we can kind of categorize the core-core clusters as having pretty low entropy profile, core entropy below this 50 keV centimeter square, whereas the non-core cores having higher entropy in the cluster cores. And very interestingly, observations have found that the core-core and non-core-core fraction is about 1:1. And that fraction is actually quite constant with redshift, which is a little unexpected because naively we would expect the non-core-core clusters to cool down to core cores over the cosmic time. However, the constant core-core fraction is telling us that some of the core-core clusters actually can be heated back to the non-core-core state throughout their lifetime. Okay, and in simulations, it has been really difficult to model this interplay among mergers, cooling, and AGM feedback because it is very sensitive to how you implement radiated cooling and feedback in the simulations. And let me dig a little more into the key factors that determines the core-core and non-core-core evolution. So first of all, like I said, due to radiated cooling, we expect the non-core-core to become core cores over cosmic time. And for core-core clusters, we also know that they need to be balanced by AGM heating inside the core-core region. However, in terms of how to transform core cores to non-core-core clusters, so some simulations suggest that they can be done by cluster merger activity, but some suggest that merger activity can only delay the onset of cooling catastrophe. And in terms of AGM heating, it's also both yes and no in previous simulations. And note that actually some of the previous simulations do not have radiated cooling or do not have AGM feedback in their work. And also, even for cosmological simulations that self-consistently include merger, cooling, and AGM feedback, some of them don't agree with each other. And also, cosmological simulations usually don't have enough spatial resolution and temporal resolution to really help us to disentangle these different physical mechanisms. And that is why recently we've revisited the problem of core-core destruction by mergers or AGMs using 3D hydrodynamic simulations of binary cluster merger simulations using the gamma code. And in our simulation, we have radiated cooling and AGM jet feedback. And we have 9 different simulations with varied mass ratios and impact parameters. So you can see 3 of the 9 simulations here. And for mass ratios, we have 1:1, 3:1, and 10:1. And for the impact parameter, we have head-on collisions and 2 off-axis merger scenarios. And throughout the discussion, I will quantify the core cores as having a core entropy within 40 kiloparsecs in the core region to be less than 50 keV per centimeter squared. Okay, and non-core core is defined by this value. And here is a, here's a table summarizing the 9 simulations that I just told you, and the default set is including radiated cooling and AGN feedback. And for comparison, we also have a merger-only run and a merger plus cooling run. So for all our simulations, we can basically analyze how the central entropy evolves with the cluster lifetime. And this is a very busy plot, so I don't expect you to understand all the curves here. But here I just want to show you that for all the simulations, we can plot the evolution of the S40, the core entropy value. And our initial condition starts from a cool core cluster. So at the end of the simulations of 10 gigayears, we can then see how the cool cores have been transformed into a non-cool core cluster, or the cool core actually remain in the cool core state. And in our simulation, we can also identify where the merger begins to occur. For example, this first vertical line corresponds to the epoch when we have the first core passage. And also in the simulation, we can also know the time when the 2 black holes merge together. So in between these 2 vertical lines, basically this is where the merger heating is most effective. And in our simulation, we can also calculate the accumulated energy from AGN and compare that with the accumulated energy for radiated cooling losses. And we use this kind of plot to see whether AGN heating is important or not. Okay, so because of the limited amount of time, let me just summarize the result using this table. So here, again, you can see we have 9 different simulations with different mass ratios and impact parameters. And this last column represents the end result at the end of the simulation. And so you can see that for some cases, the core cores are preserved, and some are destroyed by mergers or AGN feedback. And basically, what we found is that we found 3 different scenarios of core core and non-core core transition. So the first scenario corresponds to these 4 simulations, and that mainly happens when you have a minor merger with a really small or large mass ratio, so small infalling subcluster falling into the main cluster. And in this case, the core core is preserved throughout the simulation. And let's look at the entropy evolution for these 3 different cases. So basically, you can find that for these cases, actually, the merger heating is only temporarily heating the cluster core, but after a few gigayears, the cool core state is remaining throughout the majority of the cluster lifetime. And therefore, in this simulation, the merger heating alone is not enough to balance cooling, and eventually the AGN feedback is still needed to balance cooling throughout the cluster lifetime. And the second scenario corresponds to the 4th simulation, which is the head-on collision with a mass ratio of 3:1. In this case, the cool core is destroyed by the cluster merger only, and the AGN feedback plays a really minor role. So let's again look at the entropy evolution for this simulation, which is shown in the red solid line here. So you can see that right after the first core passage, actually the entropy is elevated to pretty high values and stay pretty much constant throughout the cluster's lifetime. And therefore, in this cluster, the cluster core is really heated up by the merger heating alone, and therefore there's very little central cooling and very little supermassive black hole accretion and feedback. And therefore, in this work, in this simulation, the AGN feedback is basically negligible. And we also found a really interesting 3rd scenario that refers to these 4 cases, where it's primarily for those off-axis merger simulations. And in these simulations, we find that the core cores are destroyed both by the merger and AGN activity. So let me elaborate on that. So here I'm showing you the entropy map of one of these 4 off-axis simulation right after the first core passage. So you can see that the subcluster have already fly by the main cluster here, and you can see that right after the first core passage, actually the main cluster still have pretty low entropy. And therefore, there's still some coal gas that's streaming into the central black hole, triggering AGN activity. And therefore, for some period of time, like several giga years, right after the first core passage, actually AGN heating is doing the work of heating the core. And after the infalling subcluster go back and merge with the main cluster, then the merger-induced mixing starts to elevate the entropy even more. Okay, so let's look at the entropy evolution for this run, which is shown in the blue solid line here. So you can see that right after the first core passage, actually the entropy level is still pretty low, and here the AGN heating still needs to do the work to warm up the core. And after the infalling subcluster mixes the gas within the core entropy remains pretty flat until the end of the simulations. Okay, so we found a really interesting case where the AGN, the cluster mergers and the AGNs are actually working hand in hand to transform the core clusters back to the non-core state. And this is the first time this is clearly demonstrated in numerical simulations. Okay, in summary, we performed the first comprehensive set of merger, cooling, AGN simulations with varied merger parameters. And we found that both mergers and AGNs play a role in core destruction, and their importance actually depends on the merger parameter. And then we found 3 different scenarios of how core and non-core transition occurs. So for the simulation data set that I just showed you, it's purely hydrodynamic. But in the near future, we will further include magnetic fields and cosmic rays. And these simulation suites will be a valuable data set to study the complex ICM physics. And so if you have any ideas of how to better utilize this database, I will be very happy to discuss with you. Thank you very much.
Thank you, Karen. We take questions.
Very interesting result. So in addition to mass ratio, probably how compact the core is also important, right?
Yes.
So have you looked at the different core properties?
Right, so for the initial condition, we just adopt some typical observed core cluster profile as inputs. But indeed, actually the result could depend on the initial density profile and temperature profile that we put in. So yeah, in the future, in principle, we can try to vary that also.
Thanks for the nice presentation. I have a question with something about initial condition as well. So I think this simulation can also put turbulence into this medium, and have you tested with a different turbulence level?
So we haven't really looked into the detail about the turbulence property, but that's definitely our next step.
Thank you. Okay, any further questions?
This is it's a nice talk. So this is more of a curiosity. So there is no fixed definition of what is a cool core and a non-cool core.
That's true.
And I could have taken many other things and defined a cool core and non-cool core, and every time I will get different sets of clusters which are cool core. So you have chosen entropy. Is there any reason why you have chosen entropy, or if the results will change if I use another definition of cool core and non-cool core?
Yeah, that's indeed a very good question. Actually, in the paper, we show that actually we tried different definitions for cool core and non-cool core. But overall, the scenarios that we probed actually is quite robust. So it's not sensitive to how we select the cool core and non-cool core clusters.
Okay, so thank you, Karen. Let's thank all speakers of today's session. Anything, do you want to say something?